graduate school full-time since 2015. I've actually been working in industry at a company called General Capacitor that was operating here in town, and what we made were lithium-ion capacitors. There's some floating around for your reference. And in the course of my job, I realized what we needed was a mathematical model for these that considers what the energy storage is going to be, and when it figures out what the energy storage is going to be, it needs to consider the charge or discharge current, and therefore power, Ohm's law, P equals IV. It needs to consider the constituent component parameters. You'll see you can probably store more energy in the big cells there than you can in the little ones that are next to Dr. U. So obviously that makes a difference, and we need to be able to model that somehow. And then we want this to be a dynamic model because we want to consider also how long will it take to charge it, and what is the state of charge if you're charging for 5 minutes as opposed to an hour or whatever. So that's the goal behind everything you're about to hear. And why do we need to do this? Well, often I found when I was a general capacitor that customers say, hey, I need something to store my energy. I don't care if it's a battery, I don't care if it's a supercapacitor, but I have this specific form factor. I need to deliver this much current, I need to operate at this voltage, and I'm going to need this cycle life. Can you do it? And we have a good idea for if one of our existing products could do it, but these customers are often willing to pay high dollar for a very specific form factor for a satellite or something like that. And when they do that, I had to, we had to say, okay, pause, wait a minute. It might be able to do this, but we're going to have to build some prototypes according to your form factor to get a good assessment for how well they work, and then we'll know if we're able to do it or not, and we can tweak the design. And by the time you say all that, the customer says, how about this? I'll just find a new supplier with a new product, and you lose your customer. So that's a major, from a commercial standpoint, it's a major barrier to market entry that I've got to say plagued the lithium-ion capacitor industry. So the existing models, by the way, before this research began, the vast majority only reflected experimental results, which is nice if you want to tell your customer this product will work, but if you're trying to further the state of the art, let alone design something to a new form factor for a new application, or figure out will this technology be able to meet some future need, that's not very useful. Also, the little bit of predictive studies out there were able to predict the cycle life as a function of temperature. Cycle life being how many times can you completely charge and discharge it. But we're going to see there were some major limitations of that study as well. And then, why can't we just look at our materials and estimate? Well, you're going to see the energy storage of a lithium-ion capacitor varies a lot compared to the charge or discharge power. This has been experimentally observed, but until I began this work, it really was not well understood at all. All right, so introduction. I used to get asked a lot, what's a supercapacitor? Well, a supercapacitor is a device that stores energy. Typically, it can only store a little bit of energy, but it can charge and discharge it very fast. And cycle life, some people out on the market are reporting millions of cycles, but as a practical matter, hundreds of thousands easy. As opposed to a battery, which typically can store a lot of energy, but is typically limited on the amount of current it can deliver or be charged with. And the cycle life, I've seen people reporting under laboratory conditions 7,000 cycles, but I honestly believe those are very optimistic, very safe and secure laboratory conditions. If you're doing 5,000 to 6,000 in the real world, that's very good. So, idea behind a lithium-ion capacitor is we can now, if electrochemical double-layer capacitors are over here, if lithium-ion batteries are over here, we can have a device that's in the top right of this red cone. So what the lithium-ion capacitor is doing now is improving the energy density from a traditional electrochemical double layer capacitor, but it's also improving the charge or discharge current, and therefore power, over a traditional lithium-ion battery. So how does it do this? Well, I have a cutaway here of the electrochemical part of a lithium-ion capacitor, and what it does is it marries a lithium-ion battery and electrochemical double-layer capacitor. So what we see here, this is just one of the reactive cells in the devices you're holding. Dr. Yu, we have 14 of these in here sandwiched together. But essentially the reaction is you have a EDLC cathode that allows for non-Faradaic reactions, very fast, no phase change. Purists would say it's a purely physical reaction, it's not a chemical reaction. Then on the anode side, you're taking advantage of the Faradaic reactions that characterize batteries. And so you're actually oxidizing and reducing lithium and lithium ion, or in that order. And so that is the higher energy density battery reaction. And what we find is we can adjust our energy or power same way as you would in a traditional electrochemical double layer capacitor or in a traditional lithium battery. And you're always balancing which of the two reactions is going on, and that gets confusing, as we'll see in a minute. So some of the background work on these devices. First of all, there were earlier models. The very first was a Freedom Car experimental data fit. There have been a whole bunch of Randall's equivalent circuit models, and then I'm going to talk about some cycle life studies that were the main impetus for why a new model was needed. Or sorry, there were cycle life models, and I'll talk about the energy and power relationship, which is the big driver behind this work. So 2013, Omar et al. Over in Spain, they took a lithium-ion capacitor, they did an experimental data fit with the Freedom Car model, and they looked at this LIC of various charge currents, various temperatures, and measured the energy storage. What they found is at warmer temperatures, the device stores a little bit more energy. At hot, but it has a little bit lower current. At higher current, it ends up storing less energy. So all three of these factors balance with each other to tell you how the device is going to perform. But again, this is just experimental data fit. It's not predictive at all. Also, some of my colleagues at General Capacitor and at the Air Propulsion Mechatronics Energy Center across the pond here, we were in the lithium-ion capacitor business, and we did a whole bunch of electrochemical impedance spectroscopy tests, developing these nice Nyquist graphs, and from there we could build a Randall's equivalent circuit model that does a good job of telling us how this device performs. This is very good for characterizing pre-made device, but remember, these are not predictive. So the first predictive study on lithium-ion capacitor performance was by Uno and others a few years ago over in Japan. What they found is that they took a commercial off-the-shelf lithium-ion capacitor and they changed the cycle temperature. The cycle life is very easily explained and depicted by a Arrhenius equation. And the only thing that really changes is the activation energy. As the temperature changes, the activation energy is the same, so you can very easily predict what the degradation ratio is going to be for an existing lithium-ion capacitor at a given operating temperature. But, they didn't look at the chemistry inside the device. They looked at a pre-finished device and said this is how they act. There's no part of this study do they say we think it's because they were using this sort of electrolyte or this much lithium or anything like that. The devices were never opened up. So this study and its model that it developed had some major limitations there. Now, why is this such a big deal? Well, we saw earlier with the Omar study that energy and current are inversely proportional, but I think this graph here gives you an idea of just how serious these changes are. We have two different lithium-ion capacitors. One of them, we vary the power density by threefold, and we find that decreases the energy density by threefold. The other, we increase the power density by threefold, and we find that decreases the energy density twofold. So you have anywhere from a 33 to a 50% change in energy storage after you have a 300% change in power density. And this is observed experimentally, but you can imagine why if someone's trying to say, hey, I need a lithium-ion capacitor that can meet this, and that need, if you don't know, if your energy storage can vary this widely, you want to know why, and you want to understand why, so you can figure out if this device will be successful or useful for this new application. All right, so next I'm going to give you a summary of the research I did, which then we'll get into more detail in a minute. So first of all, I started with my own study on lithium-ion capacitor cycle life, and I found that Uno et al.'s relationship with different ambient cycle temperatures has the same impacts as changing the cycle current. And so there's some proportionality between the ambient temperature of the cell and the cycle current, which the Butler-Volmer equation predicts for us, and we're going to talk about the Butler-Volmer equation a lot later on in this presentation. Next, I did my own EIS study on lithium-ion capacitors. And from this, I was able to build a baseline Randall's equivalent circuit model for the general capacitor LCA200G1, which that's those three little ones together next to you, Dr. U. And from this was my baseline. And from this baseline model, I charged my theoretical LIC at a whole bunch of constant powers from 0.3 to 120 watts and measured the energy storage. And I did this experimentally on one of those devices and compared those energy storage values. And yes, there was a delta. So there was this delta, and next I dug through literature and found earlier work where people had figured out the impacts of ambient temperature, current density, ionic concentration of electrolyte, absorption coefficients of the anode and cathode materials, concentration, intercalation material, and the electrode material, the electrode's mass, its density, porosity, thickness, a whole bunch of other variables that go into developing one of these devices, and their impacts upon a whole bunch of variables that very quickly can replace those experimentally derived terms in my Randall's ECM. Specifically, the cell temperature, using the Butler-Volmer equation, the exchange current density, the ionic diffusion coefficient, the ionic concentration that's been intercalated into the anode, the Werber capacitance of the cell, its double layer capacitance, and its charge transfer resistance. And from this, I was able to build a better model that accurately predicted the energy storage as a function of the charge current and the constituent components I just told you about in the previous slide. But this initial model did not compute the cell's voltage properly. And we're going to see this is a big deal because let's think your rudimentary battery testers, what they do is they look at the voltage. Now, of course, voltage doesn't change very quickly in a battery until the battery's about dead. But in a capacitor of any sort, voltage changes linearly as a function of the state of charge. So voltage is a really quick way to tell with these devices if it's charged or not. So we need to know the voltage if we're going to know how much energy the device can store. And as I dug a little bit deeper, I found that as the model computed the temperature values just did not, I couldn't reconcile them mathematically. And also the Werber resistance that was required to make the model accurate gave me a higher value than my EIS results. So all these three variables, or their questions surrounding them, caused me to dig a little bit further to make a second iteration model. Well, how did I do that? Well, first of all, I had to do my own in situ temperature experiment. And then from that, I could recalibrate the model and came up with a way of improving my Warburg resistance calculations. So the final model that we have now predicts the energy storage of the device within about 4% error and predicts the voltage within about 4% error. So modeling, as I said, I started out with my own cycle life study. So here's the Arrhenius degradation equation that was figured out by Uno and others as a function of temperature after just doing some simple experimental fits of some data I have from General Capacitor, where we're cycling identical cells at different currents, but at the same rates at the same ambient temperature. What I found is I also get an Arrhenius equation. And as I move the variables around in a little bit in the way of derivations, what I confirmed is that the cycle current must be proportional to the ambient temperature if my results are correct and Uno's results are correct. And we're going to see in a minute, this is predicted by the Butler-Volmer equation, which is key to the first iteration model. But before we got there, next I wanted to build my own baseline experimental model to start with. And so I took a General Capacitor LCA 200G1, and as I worked at the company, I had access to how it was made and knew what information to not publish and what was publishable, but using what was open to the public, we're able to use these as variables for later on. But my experimental work started out with an electrochemical impedance spectroscopy study, like many others have done. Here are the results. And from there, I built my own Randall's equivalent circuit model. My series resistance was 0.124 ohms. My charge transfer resistance, 0.114 ohms. Double layer capacitance, 0.2 farads. The series inductor is a billionth of a Henry, so ignore that. And then came up with a Warburg resistance of about 0.11 ohms, which we'll talk about later. And then, as I said earlier, I charged this experimental Randall circuit, and I charged real-world devices at a bunch of constant powers, and found that there's pretty good agreement at low power, but, okay, this is 3 watts here. Above 3 watts, there's some significant divergence. And so the model breaks down at high power. Now we said earlier, lithium-ion capacitors, their purpose is to exploit some of the high power properties of traditional EDLCs. And if our model's breaking down here, this is obviously an issue that is going to need to be rectified. So I ended up doing, pouring through the literature, doing a bunch of derivations myself, and finding equations I could use to represent the various elements that you would see in a traditional Randall's ECM as a function of all those constituent parameters that I had access to that went into designing that cell. Specifically, I'm going over the most important ones. My Warburg capacitance is a function of the ionic concentration of the electrolyte, my Warburg resistance, the area and thickness of my electrodes divided by the ambient temperature. And then my double layer capacitance does not depend on temperature, but is a function of the density, thickness, and mass of the electrode and the electrode's porosity, and then my separator's thickness. The charge transfer resistance is a function of the cell's ambient temperature, the number of ions in the electrolyte, which is one for lithium and the exchange current. And now the Butler-Volmer equation. As we said earlier, we found that somehow, with the cycle life study, the dynamics inside the cell as a function of current are proportional to those as a function of temperature. And if we look here at Butler-Volmer equation, we see, yeah, it relates our current density to our temperature. Specifically, exchange current times exponential of the specific surface area of the anode times 1 ion per, 1 electron per lithium ion times Faraday's constant times the voltage over potential divided by universal gas constant times ambient temperature. Minus essentially the same thing with cathode. But we can, but what I realized based on research by Dr. Zeng in the back there is that the amount of energy stored at the anode of lithium-ion capacitor is orders of magnitude higher than is the cathode. So this can be treated as zero. And therefore we can express LIC's temperature as a function of its exchange current and current density. And this equation is really key to this first iteration of the model. And then how do we compute the exchange current? Well, it is a function of the rate constant times the specific capacitance of the electrode material times the concentration of intercalation material in the electrode material minus the ionic concentration that's been intercalated. That to the specific surface area of the anode times my intercalated concentration to the specific surface area of the cathode. So that's my exchange current. And how do I compute the ionic concentration that's been intercalated? Use this derivation of Fick's law as a function of the diffusion coefficient, which is a function of the cell's temperature. And in all this, I found the model worked if I did an arbitrary fit where Warburg resistive element was 0.14 ohms. But mind you, this is 1 order of magnitude higher than my EIS study said it should have been. So, but the model energy storage looks to be accurate. I mean, error is less than 4%. Just with a questionable Warburg resistance value. But I dug a little bit more and found that the model did not accurately compute the voltage at low current. And this is a problem because voltage is key to determining the state of charge of the device. So it's not going to be useful dynamically, and we're not done yet. But seemed to work fine at high power. Voltage agreed very well. Well, that's that seemed nice enough. And then when I compared the currents, what I found is okay, at high power, when you have accurate voltage, current's fairly accurate, but at low power, when voltage is too low, the current has to be too high to make up for it. So somehow, my voltage is probably not getting computed properly. Digging a little bit further, I showed you earlier that derivation of the Butler-Volmer equation I made to compute the LIC's temperature as a function of its current density and its exchange current. But I see about 100% variability between my experimental and model values. But then, I mean, 130 Kelvin. Now the room is not that cold. It's closer to 30 centigrade, so it was closer to 300 Kelvin. So these values are questionable. But they seem to be agreeing well at high power. Only problem is now my room is between 400 and 500 Kelvin. It was not that hot. Again, we were doing this work at room temperature, so something's wrong about my temperature. And so before I threw away the model, because it had accurately computed the energy storage in the cell, I wanted to see if maybe I was manipulating these temperature values wrong, and see if it was just a matter of interpretation on my part. So that's what I'll talk about first. And the three problematic variables I had to look at was that voltage, first of all, increased too slowly at low power. Then temperature, those values were much too high at high power, but much too low at low power. And my Warburg resistance was an order of magnitude higher than my electrochemical impedance spectroscopy data indicated it should have been. So all three of these variables were suspect. And I started by deriving a method of computing the temperature of a cell as a function of its Warburg behavior, its Warburg resistance and Warburg capacitance. And I could use this value at this equation as a back-end method of checking, did the model compute temperature properly to begin with? And when I did this, I looked at the experimental results and what they indicated for the Warburg capacitance and resistance, and found, okay, yes, there's good agreement with the model at low power, but then these computations really diverge at high power. So that tells me something is getting computed wrong about the temperature. So okay, temperature's wrong. Well, let's just use these values for experimental temperature that we just computed, and see how, if we plug them into the model on the front end, how would that impact the voltage error? And maybe at least there's precision in the error, even if the error is too high. Okay, and we see there's a little bit of precision, not really a lot. So it's not really a dead ringer either way. And in order to eliminate this voltage error, it's quite possible if you increase the Warburg resistance an extra order of magnitude. Well, this is almost certainly not correct, because now we're 2 orders of magnitude higher than our experimental values tell us Warburg resistance should be. So, next thing I did is I used that back-end temperature computation off of the model's results and the experimental results, and compared them to the model's initial input. And what we should expect to see is this t-check value should match the initial temperature computation, but they don't. So this indicates that these manipulations are not working. Somehow we do not understand the temperature dynamics inside these cells. And we're still very cold, might I add. We're still less than 200 centigrade. So what to do? Well, why don't we do an in situ temperature study and actually measure the temperature, rather than guess about why it's in a superconducting range. And again, why did I do this? Well, my temperature values just mathematically didn't reconcile, and in order for the model to be accurate, it required a Warburg resistance that was much too high, and voltage was inaccurate. So what I did is I charged some lithium-ion capacitors at a constant power and measured the temperature in situ. So they're external probes in an isothermal chamber, and we collected the data on how delta T changed. And it turns out delta T does not change very much at all. At the maximum delta T value I saw was 2.25 Kelvin, or 2.25 Celsius. Now, if the room temperature is 300 Kelvin, this is less than a 1% change. And this value was achieved at a 3-watt charge. At a higher power, delta T was 0. So, as practical matter, we might be able to even treat T as a constant and not see a lot of change in the model fidelity. So this was quite a surprise. But to understand it better, I turned around, I might add, so these are constant power changes. Remember, as the voltage changes in an LIC, current has to change in order to compensate. So I said, well, let's do some constant current charges and measure how the temperature changes. And what I found is that if you have a constant current charge, then delta T is actually linear. Moreover, the slope of delta T is linear as a function of your current density. This breaks down at higher power though when delta T is just 0, but the delta T is, at least at low power, fairly easy to predict in these devices. And again, it's not very large. So that was important. For the model to be accurate, delta T's changes need to be minimal. And digging through literature, I found a method of computing the Warburg resistance as a function of the Nernst diffusion coefficient. And those values are plotted. The initial very low power Warburg resistance was 0.134 ohms. Experimentally, I found 0.11 ohms, so now we're very close. And when I plug my, when I adjusted the model to say that the delta T needs to be very small, and my Warburg resistance needs to be computed using this method that looks at the Nernst diffusion properties, I found that my voltage error, it's still a little bit higher than I'd like, but it's certainly decreased. So it gets up to high power about 15%. However, if I use the very low current Warburg resistance value, which assumes my CS value is maximized, so the maximum number of these ions are intercalating into my electrode, my error is less than 4%. So now my voltage error is accurate, and I've had no change on my energy storage. So now I have a very accurate model. So in conclusion, I started out with a cycle life study, and in that I found that the cycle current and the ambient temperature that a device is cycled at have essentially the same effects on its degradation. And we can, and the Butler-Volmer equation hints at this. Then I built a Randall's equivalent circuit model experimentally, and then replaced the experimentally derived values with theoretical values based upon the constituent components. And this accurately modeled energy storage versus time, but it was not accurate for voltage or temperature or Warburg resistance. And these inaccuracies were irreconcilable, so I had to do an in situ temperature study. And with that in situ study, what I found is that delta T's are typically very small. The most you can expect to see is about a 1% change, and at high power, 0. So depending on the situation, you may want to just treat T as a constant, and that can certainly be a good rule of thumb to check the model with. Also, I revised the Warburg resistance computation method and found a means of computing my Warburg resistance that agreed with my initial EIS experiments. And when I did all this work, now my temperature computations are accurate, my voltage computations are accurate, and my energy storage is still accurate. So we have a good model that can be used to design new devices in the future. And specifically, this is the first accurate predictive model for lithium-ion capacitors. It computes the energy storage as a function of the state of charge from the constituent components and the operating parameters. Energy and voltage are both accurate within 4% error, and this is valid for 0.3 to 10 watts on one of those LCA 200G1s, which is equivalent to 13 to 450 watts per kilogram specific energy, or specific power, excuse me. Also, I'm studying both the Faradaic and the non-Faradaic processes inside the cell. So because I'm doing that, it's valuable for a lithium-ion battery. It's valuable for a lithium-ion capacitor or any other sort of asymmetric capacitor. There is minor limitation for electrochemical double-layer capacitors because they're typically symmetrical, and with the assumption that your anode reaction is orders of magnitude larger than your cathode reaction, you can't make that assumption for a symmetrical cell. But as many cells are not symmetric, and a lot of research is being done here, I believe this is a great tool that can be used to design future technologies. So more of my specific contributions. Well, the in situ temperature study. Right now in literature, I have not seen any studies that look at how lithium-ion capacitors temperature changes as a function of the charge current, or at least not to this degree of specificity. And it found that the high power delta T is 0. Moreover, the slope is can be predicted very linearly via simple linear equation at low power. Also, I experimentally described the lithium-ion capacitor's degradation as a function of cycle current and found that you still have a very similar Arrhenius degradation with increasing the current as you do when you increase the temperature. So there's some sort of relation between the cycle current and the temperature of the LIC. And I derived an asymmetric Butler-Volmer equation to compute the device's temperature as a function of its current, and therefore exchange current. Also, I derived a method of checking the temperature of a device that has Warburg elements in it as a function of its Warburg capacitance and resistance. I revised a porosity approximation for double layer capacitance. A lot of past studies looked at a macro and micro porosity. I had to adjust for essentially an absolute porosity because of the information I had available of the materials we're using in these devices. And I computed a way to, or I derived a way to manipulate fixed laws to be used in the Butler-Volmer equation. Specifically, this equation for exchange current, that is a function of the amount of material intercalated into the electrode, which is a function of the diffusion coefficient. Publications from this work. I have one out for public availability in the Journal of Power Sources. There is another cycle life study that is under peer review right now with IEEE Power Engineering letters. And then Journal of Power Sources is also reviewing another paper on some of the later improvements I made to the model when I incorporated the in situ temperature study and the revised Warburg resistance. Other awards and recognition this research has received. The NASA ITEC program said it was one of the top 25 most innovative technologies for the second half of 2019. So we're very proud about that. And that's, in the past 2 weeks, gotten me a lot of phone calls. The one I can talk about right now is with Inspiralia. They're an organization that looks at what they believe to be very promising research areas and really good ideas that merit further research. And we signed a partnership contract 2 days ago. Can't say a lot about the specifics, but they're interested, and we're moving forward trying to carry this research forward. All right, so future work to continue to improve this research. Still have a few questions about the voltage computations that I want to explore, and then temperature still has more questions. Let me start out with voltage. So the model computes its voltage as the sum of the drop across my Warburg elements, my double layer and charge transfer elements, and a series resistor. This is just going back to that initial Randall's ECM. So these three values combine to form this value, and this is my experimental value. We find when the cell is mostly charged, it's very accurate. At the very beginning of the charge, the error is fairly high. Why is this? Well, the voltage drop across my double layer charge transfer RC element has to consider the voltage drop across my charge transfer resistance, which is a function of my exchange current. Now, that's this blue line right here. Exchange current levels off to a constant 10 to the negative fourth or 10 to the negative fifth amps per meter squared. But it does not, but it starts out initially as 0. So just think about this, when the cell's not charging or discharging, there's no ionic exchange current. So when you jump from 0 to your steady state, in those initial moments, it changes quite drastically. As it changes quite drastically, let's say it starts at 0 here, that makes this value infinity. And so that's why the charge transfer resistance, it starts out very high and then eventually finds its steady state value, and therefore has this impact on the voltage drop across the double layer capacitor charge transfer resistor RC element. So I want to study exchange current a little bit more and be able to accurately model it at the very beginning of the charge cycle. Next, so delta T. As we said earlier, it's not well understood at high power. And we've been able to experimentally derive the slope of delta T at low power, but at high power it's 0. So we have a couple of questions here. Where does it transition? How quickly does it transition? What is the temperature doing at high power? And at the end of the day, what we need to do this study are higher power testers and better, more precise isothermal chambers where we can do more precise measurements. Also, we don't know if delta T will have a greater or lesser effect on the LIC at low temperatures or high temperatures. And arguments can be made both ways. So let's just take a low temperature hypothetical. So low temperature, exchange current smaller. This has been observed many, many times. That's why it's part of Fick's law of diffusion. No secret here. But if exchange current is smaller, then fewer ions are going to be intercalated in my anode. And if that's the case, that means I must have a smaller exchange current. And if I have a smaller exchange current, well, that means I probably have a smaller current density. And so so at low temperature, delta T does not have a greater effect. It ends up having a lesser effect commensurate to the temperature. But there are ways you can make the opposite argument. So let's suppose the ambient temperature is low, but you're maintaining a constant exchange current, or a constant current density. Well then, something has to give. Maybe, so it's probably going to be the exchange current, but if you have a larger exchange current, what's going to happen? Well, maybe these relationships go in reverse. Well, we know that's not the case because of Fick's laws. Maybe the O voltage potential adjusts. Or maybe the delta T has a greater impact on the cell's performance and T changes faster. Again, I tend to think it's going to be the first scenario, but until we have some experimental data telling us, I don't want to postulate. So with that, it's time now for a further discussion and questions. And I know Dr. Meyer-Besa, you had some questions. Why don't I read yours to the committee and answer them for you first?
Yes.
Okay. So
my question was regarding your thesis. How did you numerically simulate the underlying equation, the other underlying equation in the modeling, and if there were numerical
Okay, so some of the equations I did not show, just to keep the presentation. Can you hear me? Can you hear me?
Hello?
Okay, let me turn my volume up. Can you hear me now?
Yes, yes, yes.
Okay, all right, good. Energy was computed as the integral of the the current input times the voltage output, as you saw, and it also was checked against the capacitance. Just remember, energy is 1/2 C delta V squared. Voltage was computed as I showed you a little bit ago as the sum of the drop across the series element, across the charge transfer double layer capacitor element, and across the Warburg elements. And for that, use the equation V equals current times whatever resistor it was times 1 minus exponential of the time step divided by RC.
Excellent. And you had a wonderful presentation. I have to say, a wonderful work. I enjoyed it. It was really, really great, and your accomplishments as well. So it's marvelous.
Okay, and yes, and for instabilities, the two major instabilities in the model that had to be accounted for were exchange current, because it starts out at 0 before it's steady state, and the CS value, so ions intercalated in, those are, so if that value starts out at 0 before anything's begun to intercalate, that'll confuse the model on the exchange current. So the way I accounted for those is in both situations, I told the model to start out at a value that was orders of magnitude smaller than what the actual value would be, just so that it could avoid having an undefined error and be able to continue.
Okay, thank you.
Yes, ma'am.
Okay, at this point we'll open questions from the audience.
So in your model, you mentioned you can predict voltage, power, right? So with very small percent of error. So can you predict lifetime as well?
So not yet. The cycle life study, that's I should have included that as another area that I'd like to study a little bit more. We know that current and temperature break down the device in the same way, and really that's because we saw with the Butler-Volmer equation, they're related to each other when they move ions. But that's definitely an area for more study. Right now, the studies we have are more kind of experimental extrapolations.
So your prediction of power and voltage. So voltage depends on discharging time and the charging time, right? So can you predict the whole thing or just predict the initial voltage?
Well, so for initial voltage,
Yeah.
what the model assumes is you're starting out at a specific voltage. If you look at these devices, I think they say 2.2 to 3.8.
Yeah,
Because a reason for that is because the electrolyte that they use is most stable in that range. And so it breaks down if it gets lower or higher. So you have to know that property of your electrolyte where it's stable and plug that into the model. Therefore, you assume you have a healthy cell that you're starting out with, and that's why I would charge it from 2.2 volts, because that was operationally what the device is intended for.
Okay.
And every lithium-ion capacitor has its own voltage that it would start out with. But if you know what that value is, and that's really a function of your electrolyte, you can just plug that into the model as where you need to start and where you need to stop charging.
So you mentioned that measuring the temperature is one of the innovations so you have done for your PhD. And my question is that look at your measurement. You show the temperature change at different charging power or charging density.
I did constant powers and I did constant currents.
Okay. So And so later one measurement at a high value is either at a high current density or high charging power.
Well,
So
so,
temperature there's no temperature change.
so once the current got to be above,
Maybe
Well,
it's
the
the
power
size
got to be
40,
above,
40,000.
above 5 watts, so 5 divided by nominal 3, so we're talking about 2.3 amps. The delta T was 0.
Yeah. So I was trying to understand why. Yeah, I would imagine when you charge at a high
Yeah.
power, temperature will increase a little, even more.
That's why I said it's a topic that really merits further study.
Okay. Do you have any speculation?
Well, one of the things is the capacitive behavior is acting a lot more than the battery behavior, so you have more non-Faraday reactions at higher current. So my speculation is therefore they're putting off a little bit less heat than you would see as a product of your typical Faraday reactions. But really, Dr. Yu, this is a topic that
Okay.
I want
But anyway,
I
this
want
is
more
the measurement.
measurements so that we can start trying to understand it.
Okay. Seems that your measurement results basically suggest maybe for all future lithium-ion capacitors, so they should be charged at a high power density or high current.
No,
Is that
because
right?
they store less energy.
Or they store less energy.
Yes, like I showed you earlier,
Okay. That's
you know,
true.
with that one study, you can if you can increase the charge power 3 times, and you decrease the energy storage 3 times. So really, what it comes down to, and the thought behind this, well, what was the initial motivator behind this work, was because a customer says, I have a given form factor. I'm working on a satellite or an aircraft that's worth a whole lot of money, and I have a space that's this big where I need to fit an energy storage device, and here is the current I need, here's the energy storage I need. Will your device work? That was the initial motivation. So to understand, and so if you store more energy than they're gonna need for their application, I guess that's nice, but it's not really useful. Or if you store less, that's a problem. If you can't deliver the current or power they need, that's a problem. And so what it really comes down to, Dr. Yu, is what's the application of this device? If you're coming up with a new device that that stores energy asymmetrically and experiences Faradaic and non-Faradaic reactions, would it work in such and such a scenario? And if so, what would its energy storage be? What would its what maximum current could it deliver? Now I can tell you that.
Okay. So since you mentioned about the energy storage, reversely affected by the charging speed, so basically charging current, right? So energy density, charging current goes down again. So I would expect this behavior more on the lithium-ion battery side, but for capacitor, shouldn't this dependence be less?
Well,
I just my guess. Because capacitor, I suppose the ion moves, very fast, and that's why they can deliver high power density, right?
Right.
So, and the reverse side of the charging. So since the ion moves so fast, I would expect less dependency of energy storage versus charging current.
Well, what happens, Dr. Yu, is because your ions are lithium ions, and they're able to essentially reduce and oxidize deep into the electrode material during a charge and discharge. So what you have is both the Faradaic and the non-Faradaic reactions happening at the same time. And during one charge cycle, let's say this ion, let's call him Bob the lithium ion, he may act Faradayically, he gets discharged. The next cycle, he may act non-Faradaically. And what we find is, depending upon your current, you'll have more of these ions acting Faradaically or more of them acting non-Faradaically. And so it's because you have both reactions going on at the same time, and you don't know necessarily under this current, we have, will they act more like a battery or more like a capacitor until you actually study it. That's why I did this work, and it tells you, here's your voltage drop across your charge transfer elements, here's your voltage drop across your double layer, your Warburg elements, and so there you can see, okay, so I'm 30% capacitor and I'm 70% battery today. Then you can change the charge or discharge profile, and it might give you a new result. But the key is this result is the same as what's been observed experimentally, so you can trust that your result will be accurate for whatever scenario you're trying to study.
Okay, so maybe one last question can go back to slides, maybe number 20 something. 22, 23,
Okay, sure.
21. I forgot.
Yeah, let's put it back on read mode too. Let's put the, okay, there we go.
Oh, it's 50.
I'm sorry, 50?
No, 20, maybe 21. I think you present one measurement curves. Let me see. You go more.
Here?
And more. Please go. Okay, here.
Yes.
Okay. So, and you said this whatever parameter is a capacitance change with the cycle life,
Yes.
right? And you said it's exponentially decay.
Yeah.
And is the dotted line the exponential stimulation or feeding?
Yes.
It looks for me it's not exponential, more like a linear curve.
Well, it starts out right here. So it
Okay.
goes- yeah.
I'll start from the very beginning. So the drop.
Yeah, they start out about right here. It's hard to see,
I feel like the exponential only happen in a very small, maybe in the first 1 or 2 cycles, the start all of a sudden, the very fast drop appears to be exponential. But later on, the change seems like for me is more or less a linear change.
That's correct, and that's
Okay. It's my small thing.
I mean, as the
Oh, yeah.
any exponential decay gets further along, it gets flatter and flatter.
Okay, do we have any other questions? So the audience can be excused. Okay.